And I would like to welcome you, all of you, alumni and friends, on behalf of the 140 professors in the physics department, the 180 postdoctoral fellows in the physics department, the 150 technical and support staff, the 401 graduate students reading for a DPhil, and the 780 undergraduate students. So welcome to this online alumni event. So first, some announcements and ground rules to make this a smooth experience for everybody. So first, in order to reach as many people as possible, this meeting is being recorded and may be released, probably after some late editing, via the departmental website and possibly other platforms. And for this reason, we would like to make sure that everyone in the audience is muted when they are not speaking, and to keep their video off for the duration of the talk. If you have a question, please type it in the question and answer window that should be visible to you on your Zoom screen. The questions will be relayed to the speaker in the following way. Approximately every 10 minutes during James's talk, he'll stop to pause, and I will relay a question or two to him, and he will answer them. We're doing it this way because time is limited and the audience is large, and so it'll be faster to do it like this. Continue to ask questions in the chat, in the Q&A window throughout the talk. You're also, many of you, familiar with Zoom, and you know that there's also a chat window and a Zoom raise hand tool. We're asking you to use those only for technical problems. And one of our fantastic support team that are here today will converse with you one-on-one, privately, and fix your problem. So that's how we're going to proceed. The second thing I want to do is answer a question that I got before the start of this talk, and that is, how is Oxford doing? How are we doing in the physics department during the pandemic? So I want you to know that the first thing on our minds when we think about that is to wish all of you and your loved ones safety and good health. And if you look at how we're doing, well, our lives, like your lives, have been changed. You won't be surprised to know that our academics and our staff and our students have been able to carry on most of our normal activity since we have begun working from home on March the 13th. That was the day I closed the department, 11 days before the national lockdown began. And since that time, the only research continuing in our buildings has been that of several of our biophysicists who are developing rapid detection techniques for the coronavirus. And I'm very proud of their work. Theirs is one of the many research projects taking place as part of the university's response to the COVID-19 outbreak, which includes, as you have probably heard, vaccine development, treatment, and testing. But although our buildings are almost empty and silent, seminars with lively audiences continue online through Zoom. Our committee meetings, our faculty meetings, our research group meetings, our DPhil vivas continue online as well. And we've instituted online coffee chats for our staff and our students. Grant proposals are written, submitted, and defended as normal. Data continues to be analyzed and papers continue to be written, reviewed, and published. Attendance at conferences and workshops, while virtual, has continued, and we've continued to recruit new faculty members as well. You'll be interested also to know that the departmental closing coincided with the end of Hilary term. And as I talk to you today, Trinity term is almost finished. And I'm very proud of the fact that we've been able to deliver a remarkable education online effectively. It's very important to us to be able to deliver our promise to our students of a world-class education that they deserve and they expect, And I can tell you that their response has been incredibly positive. It's in marked contrast to the students at Harvard that seem to be suing their university at the moment. What our students have found is that our professors make themselves available to help solve their problems through the tutorials. All of our lectures are filmed and can be watched online at any time convenient for a student, no matter where in the world they are. And the regular scheduled time is used for a chat online with Zoom. So all of this activity has been accomplished with an incredibly minimal amount of fuss. And I'm very, very proud and grateful to all of the academic and administrative staff and to our students who adapted so well and so quickly. So just now, before we get to introduce James, let me just give you a couple of pieces of very recent news. The first is that we have completed the hire of 8 new junior faculty. We've just put a beautiful article on our webpage, so please go and take a look at it. You'll find that these exciting young scientists, 4 of them were junior faculty at institutions in the US and Europe already, and they've jumped ship and come to Oxford, and another 4 were senior postdocs from around the globe. And I'm particularly proud that 5 of the 8 new exciting young faculty are women. We also recently, as some of you will have heard, hired Seamus Davis, the James Gilbert White Distinguished Professor from Cornell, and his specialty is quantum physics. And we could attract Seamus because of the remarkable new Beecroft building, which is the quietest place in Europe. It's isolated completely from the environment in such a way that Seamus's atomic scale experiments can be performed at Oxford that couldn't be performed in Cornell. And we're in the advanced stages also of closing in on 2 other senior hires in quantum physics. And we're investing in quantum physics because we're on the verge of a second quantum revolution. Oxford is at the heart of that. That quantum revolution would change society as we know it, and Oxford will be in the vanguard of bringing about that change to improve the human condition. The key part of quantum physics can reveal more about particle physics itself, and that might come up in the questions later today. But now it gives me enormous pleasure to introduce the speaker for today, James Dodd. So James grew up in Kent, in the southeast of England, and took his first degree in physics from Royal Holloway College, which is part of the University of London. He then came to Oxford to study for his doctorate, with the head of the Department of Theoretical Physics at the time being Sir Rudolph Piles. And the head of particle physics at the time was Dick Dallas. James's supervisor with Jack Patton, and his thesis was on high energy hadron collisions, including calculations of the production of the then anticipated charmed mesons, which were indeed subsequently discovered. After postdoctoral studies at the Cavendish, at Cambridge, and at the Stanford Linear Accelerator Center, he published the first edition of the Ideas of Particle Physics in 1984. I'll repeat that, 1984. And I can tell you that I first became aware of James when, as a student, I read that book. And it is a terrific book. And I introduced all of my own graduate students to that book too. Now, James subsequently enjoyed a career in software and finance, during which he published the second edition of the book in 1993 with Guy Coughlin, also an Oxford DPhil, and a third edition in 2006 with Bengra Piles. Yet another Oxford DPhil, also supervised by Jack Patton, who's now Professor of Particle Theory at the Cavendish Laboratory at Cambridge. The fourth edition is also with Ben, and it is in the Cambridge University Press, literally, as I speak to you now. Together with Dr. Joanna Ashbourne, James is the co-founder of the St. Cross College Center for the History and Philosophy of Physics, which since 2014 has organized a series of conferences on the subject and which sponsors scholarships and prizes in the subject. So I would like you to unmute for a second and join me in a round of applause for James. Please welcome James. Thank you very much. So James, over to you.
Grand. Well, Ian, thank you very much indeed for that introduction. obviously deeply humbled and feeling rather unworthy, and also feeling slightly more nervous than I did before my DPhil Viva some 44 years ago. But I will crack on. But first of all, I will do hopefully the technical business of sharing my screen, which will reveal my extremely cluttered desktop. I am waiting for the presentation to unfold. So I'm going to be oscillating between this mode, which has a mouse I can point to, and also the play mode, which gives a tidier screen for all. So this is a talk, obviously, the idea of particle physics, and in a bit more detail, it's the ideas of particle physics 40 years on from the time at which I decided to write the ideas, rather presumptively in those days, and then to take a stab at what things we might come to see and appreciate over the next 40. And obviously that's an extremely uncertain activity. So that's 80 years in all, and in fact we have to go back practically another 80 before that to get to the start of the subject. So basically there's a lot of material to cover, so I will canter through. The ideas of particle physics itself was written for an audience of graduates in the physical sciences, mathematics and engineering, but it was written in such a style, hopefully, that it would be accessible to bright sixth formers and indeed interested lay readers without a particular education in physics. So we'll see how we go. There is the first edition of the book, and I kicked off the fourth edition with the observation that 40 years had passed since the conception of the first, and that's a reasonable time to gauge the progress of a subject like physics, because there have only been 8 periods like that since Newton wrote the Principia, which is widely regarded as the starting point of modern physics. So particle physics, high energy physics, astroparticle physics, and cosmology may all sound very exotic, but the key starting point is the need to explain everyday matter, visible light, and the forces which interact between them. So that's the subject we'll be talking about, but first, to put it all in a bit of a sort of universal context, these are 2 representations of the universe as we see it. The top is a sort of graphical history, going back to my pointer mode. We on planet Earth are located roughly where the mouse is now, some 13.5 billion years after the Big Bang, and we are orbiting a fairly unremarkable star amongst perhaps 100 billion other stars in our galaxy, amongst perhaps 100 billion other galaxies in the universe. So that really puts us in our place in terms of significance. But traveling back through the 13.5 billion years, we believe the universe started at a single point known as the Big Bang. The universe then had to go through a still rather unexplained phase of inflation, which multiplied its size instantaneously many-fold. Thereafter, for the subsequent 350,000 years, the universe consisted largely of a very dense soup of particles and light, photons, and at 375,000 years, basically the universe became sufficiently dilute that light could escape. And the bottom picture is a photograph of that light from 375,000 years ago, known as the cosmic microwave background. The slight coloration of the oval indicate minute fluctuations in the temperature around the average, which is around 2.5 degrees Kelvin, so very close to absolute zero. And study of this cosmic microwave background basically is very instrumental in determining or discovering the dynamics behind the Big Bang. So that's starting at the universal scale, now reverting back to the start of particle physics. Clearly, all matter we now know is made of atoms, but it's worth remembering it was as late as 1900 when very reputable scientists could deny the existence of atoms. But we now know they definitely do exist, and atoms are arranged in static arrays in solids such as crystals. They roll over each other in liquids, and they fly about in a gas. And the subsequent point to note is that atoms can combine to form molecules. So water, for instance, is 2 hydrogen atoms and 1 oxygen, and it's those 3 phases of matter which constitute ice, water, and steam. And a lesson from chemistry is that all atoms are basically multiples of the mass of the hydrogen atom, as we shall come to see. So then moving on to light, Faraday and Maxwell taught us that light is basically the phenomenon of oscillating electric and magnetic fields, with the oscillations occurring in directions transverse to the direction of propagation. And the frequency of the radiation, that is to say the frequency of the waves, basically determines the phenomena we see. And so very long wavelengths give rise to radio waves, and then up to infrared for our ovens. Visible light is just a very small fragment in the middle of the spectrum, and then as the wavelength decreases and the energy increases, we move up through X-rays to the gamma rays, which we will see in particle reactions. So that's the universe, the atomic nature of matter, and the nature of light. I'm now just going to summarize the forces of nature. And I'm going to read the table, which I hope people can make out. I'll move to the full screen to make it perhaps a bit more visible. Starting at the bottom, the strong nuclear force is responsible for binding together the constituents of the atomic nucleus. It basically operates only over a very short distance, so 10 to the minus 15 meters. And particles which experience the strong nuclear force are known as the hadrons. Electromagnetism is the next strongest force, but comes in at approximately 100th the strength of the strong nuclear force. But it is effectively of infinite range, and effectively electromagnetism governs most of the phenomena of atomic physics, therefore the whole of chemistry. The weak nuclear force is one that's least familiar to us all. It causes nuclear beta decay in the atomic nucleus, whereby a neutron emits an electron and converts to a proton. So a rather obscure phenomena, but it's that process of nuclear beta decay which led Wolfgang Pauli to propose the introduction of a new particle, the neutrino, which was necessary to introduce conserve energy during nuclear beta decay. And then gravity, the most familiar of the forces, is the most familiar because it's the only force which acts at infinite range on electrically neutral matter. But as we can see, it's extremely feeble. So 10 to the minus 30 to the power of minus 39. And for the non-scientists, that's 1 divided by 10, followed by 39 zeros. So it really is extremely feeble, and its effects are effectively too weak to detect in the laboratory. So those are the atomic forces of nature. I'm going to revert to my draft form, and I'll just mention 2 of the well-known characters of the early days of atomic physics. Do excuse the Oxford blue background there. I was playing with the color buttons and unfortunately couldn't find a way to reverse it. So this is the only colored slide of the collection. But the 2 key individuals, I think, in the experimental era were J.J. Thomson, who basically put atoms of gas in a discharge lamp with an electric field across the gas. And by that method, he was able to determine that the atoms of the gas were emitting small negative particles, which are the electrons, some approximately 2,000 less massive than the atom as a whole. And about a decade later, Lord Rutherford was using radioactive alpha particles, which we now know to be the nuclei of helium atoms. But he used radioactive alpha particles to fire at a foil of gold atoms, and was very surprised to find that some bounced straight back into back towards the source, and that led Rutherford and also the renowned theorist Niels Bohr to propose the nuclear picture of the atom. So those are the early days of atomic physics, and not to be left out, Oxford's very own Henry Moseley did absolutely groundbreaking work in basically determining the electrical charge of atoms in relation to their weight, and basically established that the mass of an atom is approximately twice the number of protons in the nucleus, and so basically was able to plot the atomic number, the electrical charge, against the atomic weight. And that also allows us to plot the stability of atomic nuclei, the most stable, in fact, being the atom of iron. So those are the early days of atomic physics. That explained Mendeleev's periodic table, which ranks the chemical elements in basically in families depending on their properties. The lightest atom is hydrogen, 1 proton orbited by a single electron, and helium, the next, has a nucleus consisting of 2 protons and 2 neutrons, and surrounded by 2 electrons, and so on up through the periodic table until we get to uranium with 238 nucleons, an atomic weight of 238. And the way in which atomic physics was studied, certainly, well, you know, since the early 1900s have been by looking at the atomic spectra and the various transitions between the various electronic orbits give rise to various sequences of light emitted from atoms. So those are the early days of atomic physics. I'll now just move on to, if you like, theoretical developments of those days, which are the necessary tools of particle physics. The first is quantum mechanics, introduced by a rather stern-looking Max Planck of Germany in 1900, and to explain radiation, the way light is radiated from heated bodies, Planck had to propose that energy could be emitted only in multiples of what has become known as Planck's constant h bar. So it's the constant of proportionality between the energy emitted and the frequency of the radiation, the frequency of the light. And that gives Planck's constant units of angular momentum. And it's important to point out that angular momentum, both orbital angular momentum of electrons around the nucleus and the intrinsic angular momentum of a particle like the electron, that is to say its spin, are very fundamental classifications of particles, as we shall come to see. That's quantum mechanics, and we'll see a bit more in future. And then, obviously, needing no introduction, a picture of Albert Einstein, most probably at about the same time as he visited Christchurch on his voyage from Germany to the United States. Special relativity is based on the fact that the speed of light in a vacuum is constant at approximately 300,000 kilometers a second. And if you account for that, it's necessary to introduce the contraction of space and time, and writing down the mathematics of that eventually results in the most famous formula of all time, E equals mc squared. That is to say, the energy of a particle is equivalent to its rest mass times the speed of light squared. So those are the two theoretical elements we need for particle physics. And moving on, as a slight diversion, but as we're dealing with Einstein, now is the time to mention not only his special theory, but the general theory of relativity. And the general theory of relativity deals with accelerating frames of reference. And it was inspired by Einstein's insight into the equivalence of gravitational mass, that is, as mass appears in Newton's law of gravity, and inertial mass, which is its resistance to acceleration, as in Newton's first law of motion, force equals mass times acceleration. And those two, that principle of equivalence basically led Einstein onto a mathematical journey of 10 years. And it's astonishing to think that even Einstein had to consult with professors of mathematics to formulate his theory. But he did indeed. And one of the key predictions is that space-time becomes curved in the presence of mass, which leads to the deflection of light around mass. And that was spectacularly confirmed in 1919 by Eddington during the solar eclipse of that year. And just by way of sort of personal remark, one of the most impressive series of papers I've seen have been Einstein's pages of the 1916 manuscript, which I saw exhibited at the Max Planck Institute during a conference. And in 50 handwritten pages, he literally takes us from those very general early assumptions all the way through to detailed calculations, both of the deflection of light by the sun and anomalies in the orbit of Mercury. So a fantastic feat of calculation way before the invention of computers and simulations. So at that point, Ian, I'll just take a brief pause for a quick glass of water and ask if anyone has any pressing questions at this stage, early as it is.
If the audience could write their questions into the Q&A box that you should have visible on your screens, then I can relay them to James. The audience should not feel shy about this.
Well, Ian, that's actually a very welcome remark, as I'm aware we've spent a good, sort of 15, 20 minutes on the introductory part, but we're now going to get to the exciting part. So I will press on and pause in another 10 minutes or so.
James, let me just give you one question here that is a very simple one. And it is, will your PowerPoint be available afterwards to the audience?
I think the answer is almost certainly yes. I mean, of course, this whole the whole talk will be available on replay, and for people with laptops, which might be the same as mine, a good trick I've learned is screenshotting, which is Shift Command 3, and that actually takes a photograph of what's on your screen and stores it on your desktop. So that's another alternative. But yes, I'm sure
that's wonderful. And another question has come in as we're speaking, and it's from Elaine Galloway, who says, surely it's the case that Rutherford wasn't surprised after all he was testing his theory.
I think he was surprised, as whether it's apocryphal or not. He's reputed to have said it was as remarkable as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So I think history tells us that he was surprised, because at that stage there was a counter model of the atom, which was Thomson's plum pudding model, in which electrons are simply dotted in an amorphous mass occupying the space of the atom. In reality, we know that the atom is nearly all empty space, and in a garden party analogy, if the nucleus was a cricket ball in the middle of the pitch, the electron is a ping pong ball on the boundary.
Excellent. And there's another question came in, if I may ask it. So Robert Woolgate would like to know where he could go to see Einstein's 1960 manuscript that you've displayed on your slides here.
Right. I think I'm right in saying it's in the university in Tel Aviv in Israel. It does travel quite frequently to conferences, I think, and there is, I think, if you just put Einstein's 1916 manuscript into Google, chances are you'd be able to discover it somewhere online. But and in fact, I would imagine there is an Einstein archive at the university.
Yes, and there's another question about this coming in now from an anonymous attendee, which was that they were having some difficulty in reading. They're trying to read what's actually written there, and they couldn't make it out very clearly, and they're wondering if it's in German or English.
It's in German.
Yeah, that's what I thought. That's that question. That's a good question too. Okay, we've ended. There was a question that came in at the very beginning, but I'm holding off on that one because it's about axions and the recent observation. I thought we should save that one for the end, but that's incredibly important. It would fit better towards the end of the talk.
Yes, by the time we get to axions, we'll be halfway through a jug of pins, I think.
Excellent, excellent. Let's go back to the talk then, James. Thank you.
We'll get there. Okay, well, that's the early easy stuff. Let's go on to something a bit more challenging now. So if you put relativity and quantum mechanics together, you get relativistic quantum mechanics. And the formula we looked at, E equals mc squared, is a simplification of a more general formula for moving bodies, which is the energy is, going into my pointer mode, the energy is plus or minus the square root of the momentum squared times the speed of light squared plus the mass squared times the speed of light to the power 4. That is just the E equals mc squared component, but with a moving particle, you've got the p squared c squared. Now, the fact is, there is both a positive and a negative solution to that equation. And the genius of Paul Dirac here was to say that, in fact, those negative energy solutions do actually represent something. And he took them to represent antimatter. So in an absolutely astounding sort of leap of intuition, he proposed that the real world, full of electrons spaced out in their various orbits or physical states, separated by the Pauli exclusion principle, hover above a fully occupied sea of negative energy electrons. Because they're negative energy, we really don't notice them. However, when an energetic photon propagates along and strikes a negative energy electron, it's promoted to a positive energy, given sufficient energy in the photon, leaving a hole behind in the C, the negative energy C. And he interprets the absence of a negative energy electron as the presence of a positive energy anti-electron, which he calls the positron. So here is a diagram of the photon propagating, dissociating into an electron and a positron. And in fact, because of momentum conservation, it needs to do so nearby a nucleus. But that was Dirac's prediction of antimatter. And also, in a more mathematical remark, the symbol for the wave function of the electron is not simply a simple probability, it's a 4-component object, and that refers to the probabilities of the electron and the positron being either spin up or spin down. So the Dirac equation actually predicts that the electron will have a spin of 1/2 unit of Planck's constant. So that's this is the start of the modern fun, as it were. On the basis of the Dirac equation, it's possible to formulate the theory of quantum electrodynamics, which is basically the interaction of charged particles. So it's necessary to think of all the possible ways that charged particles could interact, and this is done by the method of Feynman diagrams, named after Richard Feynman, the famous and extremely ebullient American physicist of the second half of the 20th century. So here we see an electron scattering off a positron by the exchange of a photon. Here we see an electron annihilating with the positron into a gamma ray loaded with energy, and then higher order Feynman diagrams correspond to more complicated processes. Key point is each vertex is multiplied by the fine structure constant, which is the intrinsic strength of the electromagnetic force, which, as we saw previously, is approximately 1/100th relative to of a strong force, that means the increasingly complicated diagrams become much, much less significant numerically. So it's possible to calculate the probabilities of the interactions on just the first few terms of the Feynman series. So that is the theory of quantum electrodynamics. At around the time that Dirac was formulating his equation, or slightly after, he was awarded not only the Nobel Prize, but also the joy of discovering his positron being discovered by Anderson in cosmic rays. And these are photographic plates taken to the top of mountains which detect elementary particles arriving in the Earth's atmosphere, which can be detected in photographic emulsion. So 1932 sees the discovery of the positron, and it was also the year in which Chadwick isolated the neutron in the Cavendish laboratory in Cambridge. So as of 1932, the material world consists of protons and neutrons, which combine to form the atomic nucleus, the electron, which determines the chemistry of the atoms, and then Pauli's neutrino, which you'll recall we had to introduce to conserve energy during beta decay. So in 1932, if the world had basically gone a different path, we would be able to describe nature almost perfectly, just on the basis of these particles which make up the known phenomena we observe here on Earth. However, nature had some intriguing further phenomena to show us, and apologies for the rather sort of spider-like nature of these diagrams, but I've spent hours over the past few days lifting diagrams from the book and trying to make them visible. But again, from cosmic rays in the 1930s and 1940s, there were three key discoveries. One is a particle called the pion, which is a strongly interacting particle, decays or can decay into two gamma rays, which then decay into electron-positron pairs. The pion can also decay into the muon and a neutrino. So, the muon basically was found to be simply a heavy version, a heavy brother of the electron. So enjoys the electromagnetic force and the weak nuclear force, but not the strong force. And then, not illustrated here, but also in cosmic rays, were discovered strange particles, and these were strange in that they always were produced in pairs. And this was taken as being the production of a particle and its antiparticle, excuse me. And on the basis of them being produced in pairs, that led Abraham Pais to denote them as strange particles and award them a new quantum number called strangeness. And on the basis of that, these discoveries, we can summarize the known particles in the mid-1950s by this table I drew up in the first edition. Along the top, we have the forces of nature: weak and electromagnetic, and weak, electromagnetic, and strong. And here on the vertical axis, we have the mass. So way down at the bottom, we have the neutrino, which is actually on the zero mass point of the scale. And then just slightly off the axis is the electron. Above that, his heavy brother, the muon. The pions weigh in a bit more massive, but these are the first particles in mass which experience the strong force. Then we have the strange particles detected in cosmic rays, and these, the kaons and the pions, are known as mesons, meaning middle weights. you then come to the neutron and the proton experiencing strong electromagnetic and weak forces, which together are known as nucleons. And then when the heavier particles carry strangeness, they're known as hyperons. And together these are called the baryons. And it's just worth remarking that the electron and the neutrino are particles which come in half multiples of Planck's constant, so they're called spin half particles, and the neutrons, and as do the neutrons and protons, but then the pions and various other particles have integral spin in units of Planck's constant. And in the same way that we can calculate the interaction between electrons and positrons by quantum electrodynamics, we can also draw similar diagrams for the strong interaction and the weak interaction. The weak interaction, say between an electron turning into a neutrino by the emission of a particle rather like the photon, but to account for its very short range, it's known as an intermediate vector boson, a W boson, which has to have a very significant mass. And then modeling the strong interaction, two protons can collide by exchanging a pion between them as a so-called quantum of the strong interaction. However, whereas the weak interaction is truly fundamental, the strong interaction here is not, because it became increasingly clear that the proton is quite an extended object and most probably has constituents which became known by the name of quarks, named so by Murray Gell-Mann, after a rather obscure reference to a novel by James Joyce. But there we go. Right, so we've seen one way of classifying particles. Here is another, and these are the internal symmetries of the strongly interacting force. And effectively what we are doing is plotting electrical charge on the horizontal axis and strangeness on the vertical axis. There's slightly differing definitions, but these patterns are generated by a branch of mathematics called group theory. They're special unitary groups of dimension 3 in this particular case. And the point in emphasizing this is that on the basis of that mathematical theory, it was possible to predict the existence of the omega minus particle, which is very unusual, having strangeness -2, and that particle was duly discovered in one of the early accelerator experiments, I believe, in 1963. So moving ahead, another interesting feature to a move from that classification of the particles is that certain of the particles seem to require the quarks, 3 identical quarks, to be behaving identically in the same place at the same time, which is not allowed by Pauli's exclusion principle. So in the late 1960s, early 1970s, there was the introduction of yet another system of quantum numbers, which went by the name of color. So each of the quarks, up, down, and strange, comes in the varieties of red, green, and blue. And so the omega minus particle here basically it has 3 seemingly identical quarks, but with the introduction of color, they can be distinguished, which is the key point. So on the basis of the symmetry classification, we are building up a picture of the proton consisting of 3 quarks, and in fact the pion, it turns out to be not fundamental, but is basically a combination of a quark-antiquark pair. Two groups of experiments in the 1970s really confirmed the physical reality of quarks, and it's worth remembering this was not always the case. Certainly when I arrived in Oxford, I was told to keep an open mind, I was advised to keep an open mind that quarks may or may not exist as physical entities, but at the very least they were a very useful way of accounting for electric charges and strangeness. However, 2 classes of experiment changed all that. The first, a deep inelastic electron-proton scattering. So imagine an electron skidding over the top of this chart and emitting a photon which collides with a nucleon. When the wavelength of the photon is large, it basically scatters off the nucleon as a point-like particle with a very simple formula. When the wavelength of the photon becomes smaller, that is to say higher energy, it distinguishes a spatial extent of the nucleon. And very impressively, when the wavelength of the photon is very small, it starts to revert to the simplicity of point-like scattering, and that is indicative of the point-like nature of quarks within the proton. And the quarks are held together by hypothetical particles called gluons, which are the strong interaction equivalent of the photons. The other class of experiment, which was extremely dramatic, were electron-positron annihilation experiments of the sort I mentioned previously. And in particular, it's possible to measure the ratio between an electron or positron undergoing a purely electromagnetic process and transforming into a muon and an antimuon, or the photon resulting from the annihilation basically converts into a quark-antiquark pair, which gives rise to a spray of hadrons. And the ratio between these 2 events is in fact a measure of the number of quarks that there are in existence. And the dramatic result from 1974 was that the ratio suddenly jumped due to the energy of the photon being sufficient to unleash a new quark pair, the charmed anti-charmed quark meson, known as the psi meson, which was discovered in 1974. And it was that production mechanism that I studied as part of my thesis. So on the basis of that, we arrive at the standard model. And the standard model, this is taken from the CERN website, so it should be authoritative. We have the up and down quarks, which constitute the proton and the neutron. So a proton is up, up, and a down, and a neutron is a down, down, and an up. The electron is the familiar thing which orbits the atomic nucleus, and the electron has its own type of neutrino, the lepton neutrino. The strange quark was behind the production of the strange particles I referred to earlier, the charmed quark I've just mentioned. So this was forming a second generation, which explained the presence of the muon, because that's the second generation lepton. And that has its own associated neutrino, which basically a muon will decay into a muon neutrino, but not into an electron neutrino. And then in very short order, and really very surprisingly, in the mid-1970s or late 1970s, a third generation was discovered, consisting of a bottom quark denoted bottom, and surprisingly its heavier brother is the top quark. So we have a top quark and a bottom quark. A tall meson, which is an even more massive version of the electron, was discovered, and that too has its own type of neutrino. And over in this corner we have the photon, which mediates the electromagnetic force, the W and Z bosons, which motivate the weak force, and the gluons, which mediate the strong force. And just to explain in further detail, the first formulation of the standard model basically assumed massless particles, and a mechanism has to be introduced to provide the mass, and that is the famous Higgs boson, which was introduced by Peter Higgs, Tom Kibble and others, Englert and Breut and co-workers. The Higgs field, of which the Higgs boson is a particular quantum, Higgs field pervades space, giving mass to the particle. So it can rather be thought of as a modern version of the ether, and the mass of the particles is generated by their resistance to moving through the ether of the Higgs field. So at that, I'm going to stop there and ask Ian if any further questions at this stage, and I will most probably...
Well, yes, indeed, there were. In fact, just before you came to the page in which you showed for the first time the eponymous Higgs boson, there was a question: where does it all fit into it? How does the Higgs fit in? So do you want to say just a little bit more about that at this point?
Well, as I say, the original formulation of the theory, there are, in fact, the standard model consists of three theories. One is quantum electrodynamics, as originated by Dirac. One is the so-called electroweak force, which is the force mediated by these bosons, which was known to have a mass to ensure that it was only a short-range force. The gluons, like the photons, are effectively massless. To generate the mass, it was literally necessary to introduce a new field and a new particle, and it is the coupling of the quarks with the Higgs boson which gives rise to their mass. So I will say more in due course about the discovery of the Higgs boson, which was eventually discovered in 2012.
Indeed. So let's go to a couple more questions from the audience. Another one from Andrew F. is: why do physicists sometimes state that the strong force is mediated by pions and sometimes by gluons?
Right. The answer is the mediation by pions is basically a historical sort of heirloom. It was known that electrons would interact by the exchange of a quanta. So I believe it was Yukawa proposed that the strong force would be intermediated by a quantum of the strong field, which basically he called the pion. And eventually they did indeed discover the pion. But we now know, because of the discovery of the point-like nature of the quarks within the proton, the fundamental description of the strong force is that of gluon exchange between quarks. That's the real picture.
Right, thank you. There are more questions, but I propose to hold off on them because they're anticipating things that are going to be coming up in a few slides.
Right.
So let's hold off on the further questions and go back to the slides, if that's okay, James.
Good. So, well, I'm hoping that we're all still with us and getting to the exciting part of the Pim's jug, as it were, as what I'm going to do now, in my extremely young and foolhardy way, I proposed, in fact, I've called them notable milestones here, but actually I sort of described them in the first edition as probable Nobel prizes. And so I thought an interesting exercise is to go back after 40 years and see which ones turned out to be true and which ones are a bit missing. So for the first one, this was a real cheat on my part, in that we're talking about the discovery of the W and Z bosons. These are the particles which mediate the weak nuclear force. This was, the WZ bosons were discovered in 1983 at the super proton synchrotron at CERN, and this is a diagrammatic map of the sort of succeeding generations of accelerators at CERN, getting higher and higher energies. So we start with the original proton synchrotron, go on to the intersecting storage rings, which had an energy equivalent to about 30 times the mass of the proton, and then up to the super proton synchrotron, which had an energy range up to almost 300 times the mass of the proton. And so it was able to produce pairs of W bosons which weigh in at about 80 times the mass of the proton, 80 GeV. Sorry, I should have explained for the lay audience. GeV stands for giga electron volts, and it is approximately the mass of the proton. So the superproton synchrotron was able to produce pairs of Ws, and on the cover of the first edition, this is basically a image of the production of the first of the W bosons in the UA1 detector at the superproton synchrotron. So that is cheating to award myself a point for that, but nevertheless, that's life. Glue balls the idea is that because of the particular nature of the strong force, it should be possible for gluons to stick together in a way that photons don't. And that should give rise to glue balls. And I think there is nothing wrong with that in theory, but there's a lack of discernible signature by which they might be produced in accelerators, although I think the emergence of the jet structure of some particle showers does go some way to support that. Another one which was on the list and is still on the list is the decay of the proton, which is the most stable of the baryons. In fact, so stable that its likely lifetime is longer than that of the universe. So we have not detected a proton decay, but it can be permitted in certain theories. Once we get onto the Higgs boson, we are on to more solid ground. And yet again here, we're visiting CERN. This is the Large Hadron Collider, 27 kilometers in circumference, near Geneva in Switzerland, and this is one of its massive detectors. I thoroughly recommend a visit to CERN for anyone interested in this subject. These detectors are approximately the size of cathedrals full of electronics, deeply impressive. And lo and behold, yet again, the third edition of the Ideas of Particle Physics actually had a representation. It was a simulation of a Higgs event that would be seen in one of the detectors. So that was discovered in 2012, and duly Peter Higgs and another proposer of the mechanism, Englert from Belgium, were both awarded the Nobel Prize in, I think, 2015. So onwards, the top quark, I'll spare you yet another sort of particle diagram, but that was eventually discovered in 1995. The top quark is deeply interesting. It's 175 times the mass of the proton. So basically this quark, this supposed point-like particle, is in fact heavier than most atoms. It's sort of 3 times the mass of an iron atom, almost as heavy as lead. So it's quite an amazing particle. It wasn't, the discovery of it wasn't awarded the Nobel Prize, but in fact, theorists who had predicted the third flavor of quarks, the third family of quark flavors, were awarded the Nobel Prize. Magnetic monopole has not yet been seen, although it is possible to exhibit magnetic monopole effects in solid state physics. And again, for the lay audience, a magnetic monopole is like a north pole without a south pole attached to it, which basically is not part of everyday life. So that was magnetic monopole. Then on to neutrino oscillations. This is a very interesting phenomena whereby, despite my saying that an electron neutrino could not change into a muon neutrino, the answer is they can. And this was detected by the Solar Neutrino Observatory, in fact the Sudbury Neutrino Observatory. Neutrinos from the sun will be exclusively electron neutrinos, but in their passage to Earth, a large number of them seem to go missing, and that was regarded as a great puzzle until it was realized the electron neutrino might be oscillating into a muon neutrino, and experiments were conducted, and the phenomena of neutrino oscillations was indeed confirmed. This is significant because it implies, forgive me, that the neutrino has a very, very small mass. So its mass is not 0 after all, but just a very small number. And that implies there is a new branch of physics beyond the standard model, which has yet to be formulated properly. And then free quarks. At one stage it was thought it might be possible to see individual quarks outside the proton. That was realized to be not the case. The quarks can act as free, but only within the confines of the proton. And that can be discovered by looking at the effective strength of the strong nuclear force I referred to earlier as just being a constant number. In fact, the strength of the nuclear force depends on the distance at which you view it. So the higher the energy of a process like a particle collision, the shorter the distance you're probing. And once you're probing at very high energies, the quarks behave as if they are actually free. So that's was given the name of asymptotic freedom, for which 3 US theorists were awarded the Nobel Prize in the 1990s. Now, we're coming to more interesting ground, supersymmetric particles. And I'm afraid I've just been rather sort of parenthetic about this because we're getting into fairly exotic territory. I referred earlier to the top having the top quark having a fantastic mass of 173 times the mass of the proton. Here are the imputed quark masses which I will confess to having abstracted from another textbook. But we can see these supposedly point-like particles have a fantastic range of masses. And to formulate a theory which can come anywhere close to resolving this so-called hierarchy problem, we have to take the standard model, as illustrated a bit more graphically in previous slides, and then assume there is another entire universe of supersymmetric particles where all the angular momentum of the particles is shifted by 1/2 unit of Planck's constant. And you start getting into a wonderful sort of dictionary of particle soup here. So a spin half Higgs particle is a Higgsino, the quarks become squarks, and the leptons become sleptons, including a selectron and a smuon and a neutrino. The gluons become gluinos, and of course the W's become winos and xenos and photinos. So it's rather an expensive way to solve this particular puzzle, proposing that there is an entire new universe made of supersymmetric particles, and rather like the generation of the mass I referred to by introduction of the Higgs field, you have to assume that the supersymmetry is broken so that the existing universe we see is of relatively, the particles of the standard model are these masses we've seen here, but that the masses of the supersymmetric particles are more massive even than the ones shown here. And so this diagram here, there are other technical reasons for introducing supersymmetry, in that it allows the calculation of Feynman diagrams in these advanced theories much more easily. So that's supersymmetry, work in progress. But the 10th of my projections was the discovery of gravitational waves. Now, this is very interesting. Einstein predicted gravitational waves in his 1916 theory, but then he thought he'd got it wrong. And so he wrote a paper in 1932 saying, sorry, I was wrong, gravitational waves don't exist. So the American referees sent it to referees, and or the American journal sent it to referees, and the referees said, actually, Professor Einstein, you were correct in the first place. Gravitational waves do exist. So there then followed a century-long hunt for gravitational waves. For a while, they were tried to be detected in the laboratory, and in fact, at Stephen Hawking's 70th birthday celebration, I believe one of his colleagues referred to one proposal in, I think, the early 1970s, possibly the 60s, whereby he actually proposed an experiment to try and detect gravity waves in the basement of the old Cavendish laboratory in Cambridge. And in fact, the grant awarding body decided that was a bit ambitious, so that didn't go ahead. Anyway, the bottom line is gravitational waves arrived with a real bang in 2015, thanks to LIGO, the Laser Interferometer Gravitational Observatory. And basically this consists of two arrangements, such as the one illustrated here. That's a 3-kilometer laser beam, which interferes with another 3-kilometer laser beam. And as a gravitational wave travels through those beams, it causes the most minute flexing of space. So the equivalent of the width of a human hair between here and the nearest star. So it's 1 part in 10 to the minus 20. So fantastically accurate apparatus. There's one located in Washington State and the other, I think, in Louisiana. And the fact that they both saw the wave at the same time confirmed it was real. Here is a graphical where did the gravitational wave come from? Well, incredibly, it came from two black holes colliding approximately 4 billion light years away. The energy had been traveling through open space for 4 billion years and eventually arrived in Washington State in 2015, still with enough energy, rather broadly speaking, equivalent to a mobile phone signal. So the amount of energy emitted, what happens is that black holes are circulating around each other. They eventually begin to rotate extremely rapidly. They merge and then settle down into a single bigger black hole. Each of these black holes was 30 times the mass of the sun. In the final seconds, it was rotating at approximately half the speed of light. So, you know, an incredible cosmic event. And so the detection of this signal, firstly, it was the first observation of a black hole, as well as being the first observation of the gravitational waves. And this is going to be a fascinating field in future. They are planning to launch a constellation of 3 satellites, which will greatly increase the range at which these waves can be detected, and therefore the event rate. So come the launch of these, it is in 2035, it's anticipated that we'll be seeing tens of thousands of black hole collisions from the depths of the universe, all arriving on Earth. So those were the 10 original points. I then asked the question, what's missing, or what did I miss in 1980? And 2 notable things, which I hope I'll be forgiven for. One, interestingly, is the World Wide Web. This is a schematic diagram of the CERN's internal telephone directory, which was effectively made amenable to internet search by our very own Oxford alumnus, Tim Berners-Lee. It's one of the great spin-offs of all time, is that the whole field of particle physics gave rise to the World Wide Web. So that certainly paid for the CERN budget many thousands of times over. The second thing, I didn't quite miss, but another development of recent years has been string theory. And during my years in the department, strings basically referred to quark line diagrams, which effectively are now taking the place of gluons. So that was the origin, called the hadronic string. I was quite surprised some years later for people to propose that all particles, including quarks, are actually made of strings, extremely small strings. And the modes of vibrations of the quarks give rise to the spectrum of masses of the quarks we referred to earlier. So string theory has become almost like a religion. Last seen, there are about 15,000 papers have been written on it, but unfortunately it has yet to provide a testable prediction. One complication of string theory is that it's formulated in 11 dimensions, and so you have to compactify 7 of the dimensions to get to the 4 we have, 3 of space, 1 of time, and the number of ways of doing that generate hundreds of millions, 10 to the 10 ways of compactifying the so-called space to eventually determine which universe we're living in. So that's string theory. So I would at this point ask questions, but in fact I'm I can hear a cheer, even though everyone is on mute. This is the last slide. Prospective milestones for the next few decades. And I'll be brief, and I haven't got lots and lots of pictures to accompany these, but supersymmetric particles are still outstanding. The Large Hadron Collider is being upgraded to the HL LHC, so the large, high luminosity Large Hadron Collider. So that will generate many more events, and it's hoped that in mining the data from those events, we may detect evidence of supersymmetrical particles. Axions were mentioned earlier, and they're very interesting. There is a technical problem with the standard model, which is to do with the symmetry of particles under charge conjugation and mirror reflection. And it is noted that the violation of those symmetries by the strong force is an outstanding problem, which can be solved by the introduction of new particles called axions. So rather like we introduced the Higgs to generate massive particles, we're introducing another field, the axions, to solve this problem of the symmetry of particles. These are likely to be very light. They will be spinless like the Higgs. So in some sense, they could well act as sort of cosmic sludge in the universe, which basically might explain some puzzles in the universe, which I'll come back to in a minute. Here, there are plans for at least 3 large new accelerators, which I won't go into in detail, but there's the Future Circular Collider proposed for CERN, which will be an even bigger machine, currently under consideration. There's an international linear collider proposed for Japan. And then a very interesting project is the Chinese electron-positron collider, which is currently under planning. And I could imagine, bearing in mind, you know, the controversies over technology and relations between China and the West, that will be something of a flagship project. So other things to look for, basically there's a clump of experiments looking for physics beyond the standard model, and they are to do with how the muon behaves as a magnet, whether the neutron, despite being electrically neutral, might display characteristics of an electric dipole because of the charges of the quarks within it, and various other phenomena. So all those are actively under investigation now. We would like to see some predictions from string theory, but as I've mentioned, it's now the best part of 40 years people have been producing papers on string theory with no firm prediction. I should have inserted another bullet, which is to do with the dark matter in the universe. The observable universe only consists of about 5% of the mass of the universe we can determine from the motions of galaxies. So what the missing matter is an open question. It could be axions, it could be black holes, or a mixture of the two, or indeed supersymmetric particles. So there are quite a few candidates. The data produced in high energy experiments is absolutely prodigious, and so, you know, high energy physics is on the cusp of machine learning, particularly in pattern recognition in particle physics experiments. And then slightly sort of left field I've included here is privatization. I'm thinking in the era where Elon Musk and SpaceX can launch private space missions, why shouldn't we have a CERN-X? Any of the major technology companies, or indeed any of the larger financial investors could quite feasibly finance a laboratory such as CERN. And bearing in mind the spin-offs I've mentioned, that might make eminent sense. And already ITER is the international experiment for fusion research. We already have private companies researching nuclear fusion, such as Tokamak Energy near Oxford. And I will stop at the wider world. The point on the wider world is to say that happily the physics community has built this huge body of knowledge and these enormously elaborate machines, and generally speaking have done so on time and budget. And it would be nice if some of that expertise could be perhaps shared with less successful ventures to do with public IT systems and the scientific management of society generally. So on that rather sanctimonious note, I'll stop and take questions.
James, thank you so much. That was absolutely marvelous talk, really marvelous indeed. And of course, if people had been able to unmute themselves at this point, they would have given you a round of applause, but they can't. So I should just clap my hands a few times to indicate the enthusiasm from all of us.
Thank you very much, and I hope I didn't go on too long.
No, not at all.
We've still got 240 people, so
that's right.
Thank you for staying the course.
Absolutely, absolutely. And of course, many of these 240 people have questions, and I want to go through just a few of them now, and the others will be answered by email later. So let's, I've been asked to turn on my video too, so I will do that, if you can see me.
Hello, Ian.
Right, okay, so I am really here, and I listened throughout, James, and it was fantastic. So let's go to some questions. One of the ones is from Tom Adams. He says, are we any closer to understanding why the electron, which is an electron, has exactly the same magnitude of electric charge as the proton, which consists of 3 quarks?
Not off my head, no. There is, the answer is there may well be a fundamental reason, but unfortunately I can't quite recall it at this very instant. There are, some very fundamental questions where there aren't necessarily definite answers. Like I noted in the standard model, there are 3 families of particles. A good question is why 3? Why not 5 or 100? And those are unanswered questions. In fact, I did recently see a seminar given by our very own John March Russell, who I think was suggesting that new quantum theories of gravity might actually be pointing in the direction of limiting fermion families to the number 3. But off the top of my head, I can't explain why, for instance, the charge or the charge on the electron is 3 times the charge on a quark.
Yes, no one can at this time, of course, but we hope in the future that we'll have an answer. You're absolutely right. So, in a similar vein, a question from Edward B. What are particles such as electrons and quarks made of?
Well, that's a very good, that is a very good question. And the answer is, you can take your choice. In quantum field theory, they are point-like particles, so they're not made of anything. They are a point. However, points are very problematic mathematically, because if, let's just say, you have 2 point-like particles at the same place, then when r is 0 in the denominator the strength of the force is infinite, and the same would go for electric charge. That's a well-known problem in quantum field theory and is solved by the mechanism of confinement. And solved by the phenomena of renormalization. In that theory, basically the particles we observe are dressed up points surrounded by quantum fluctuations in the vacuum. So that's one rather long-winded answer. The other possibility I've just mentioned is they're made up of strings, but then the question becomes, well, what's a string? We're talking about the very sort of fabric of space and time, and indeed there's an alternative to string theory called loop quantum gravity, which is very interesting. Heisenberg's uncertainty principle basically says, you can't be precise as to a particle's position at the same time as being certain about its momentum, which means really that the notion of a point is something that can never be actually realized in practice. So on that basis, space and time itself might be divided into extremely small cells, and that is referred to as a space-time foam. And there are proponents such as Carlo Rovelli and Lee Smolin, who pioneered that theory of loop quantum gravity. But again, I think there's the implication you might be able to detect in anomalies in the propagation of light across the universe. But that's about as far as I can go with that one.
Thank you very much. Another question, there were a number of questions that were quite similar and related to your answers, so I won't ask those ones, but instead I would ask the following from Robert Rutherford. I've never studied group theory. Is it possible to say why it is so powerful in fundamental physics?
Yes, or at least I'll give my view. And then I will, yes, my view is fundamental to particle physics is the notion of symmetry. And there are at least two sorts of symmetry. One are internal symmetries, which is to do with the quantum numbers I mentioned and the patterns it generates. And then there are dynamical symmetries, such as symmetry of displacement, i.e. an object looks the same in London as it does in Oxford, or rotational symmetry, which means that, say, a planet orbiting the sun appears to be rotationally symmetric. And each of those dynamical symmetries results in a conservation law. So conservation, the symmetry of displacement leads to the conservation of momentum. The symmetry of rotation leads to the conservation of angular momentum. And the symmetry of time leads to the conservation of energy. So group theory describes arrays of objects which can transform into each other under the operation of the symmetry. And so that branch of theory, group theory, basically translates the symmetries into conservation laws. And in fact, that also is a fascinating story. The map between symmetries and conservation laws is due to Noether's theorem, attributable to Emmy Noether, who certainly should have a major motion picture made about her anytime soon, as being one of the very unsung heroes, feminine heroes, of early theoretical physics. If I could at this stage, I'll just, in the words of the pub landlord, if I don't know the answer, I might know either a man or a source who does. and two little advertisements, if I might. One is the pithily named Saturday Mornings of Theoretical Physics, which have been in progress now for 3 years, and they happen 3 times a year. And if you can get to the site just by tapping Saturday Mornings of Theoretical Physics into Google, and under the button labeled events, you'll find therefore approximately 15 mornings of seminars, some of which deal exclusively with group theory or the Higgs boson or accelerators or machine learning in physics. So all that's entirely free. Any member of the public can tap in Saturday Mornings of Theoretical Physics and press on the events, and the seminars are there totally free to watch. The second advertisement, if I can really press on people's humour, is the St. Cross Centre for the History and Philosophy of Physics. And that is originated with myself and Joe Ashbourne at St. Cross College. That also has approximately 5 years of day-long conferences on major topics. The last one, just hiding here, is on the science of big projects such as CERN and ITER and the Manhattan Project. And basically it covers a huge number of concepts and projects in physics, all the way back to astronomy in the medieval world, and in particular the role of the famous Merton calculators in who almost got as far as Newton's calculus, but not quite. And just hiding there, there's Schrodinger's cat.
That's great. I mean, we should take just one more question, James, but before we have to close with a toast. And so several people asked about gravitons. Are they real in your opinion? How do they fit in?
Gravitons would be the quanta of the gravitational field, and therefore the quanta of the gravitational wave. And just as in field theory, an electron is an excitation of electron field, a graviton would be an excitation of the gravitational field. Now, the point of the standard model is that the up-down quarks, the electron and the neutrino, are effectively different manifestations of the same unified field. And the quest for a quantum theory of gravity is to be able to basically incorporate a picture of gravity along the lines of the standard model. But that's basically proving to be extremely difficult. That is why string theory, one of the major motivations for the development of string theory, is that it naturally generates particles of spin 2, and because gravity is always attractive, that requires the gravitino to be spin 2. So there are connections, but there's not an answer. However, if I can, at this stage, just end with one final advertisement, for which, forgive me, yes, it had to come. Thank you for listening.
Thank you, James. Thank you so very much. Thank you. Thank you.
Very welcome.
I want to just close this meeting by saying thank you to everyone that joined us. There's still 200 people on the line, but everyone will have to go very quickly now. So I just want to say that despite the fact that we live in very challenging times, that we should all remember that the future of humankind is bound up with the ability of physics to solve problems. Physics is the great problem solver. It has demonstrated that time and time again, and I believe that science in general, and physics underpinning so much of science, will enable us to get out of our current difficulties and give mankind a much brighter future. And so we should drink a toast at this moment. This is a garden party. I have a cup of tea here, James may have something in his hand too.
Well,
Others, I hope, raise a glass as well.
I put myself off from the PIMS, but I've got
right.
lined up in the very near future.
That's right. I decided not to have the PIMS until later tonight. But the toast is to what else but Oxford Physics, to Oxford Physics.
Cheers. I'll certainly
Cheers. Thank you everybody for coming today, and I hope we'll have another event like this very soon, which you can join again. We'd love to have your feedback. We are very sorry we couldn't answer all of your questions in real time, but we will get answers to all these great questions afterwards. And James, you will make your slides available too, I think.
I will indeed.
Thank you very much. And goodbye, everybody. Take care.
Cheerio.